it takes an input and it basically spits out an output. Now it turns out that the transformation essentially takes an input vector rather, right? So it's basically to multiple tuple, and then it takes that as an input, and then the transformer, which is denoted by T here, outputs something by transforming this input. So it takes this as an input and then it essentially spits out some output, right? So in that sense, the linear transformation or transformation that we have essentially takes an input, which is a vector format, and output vector that is transformed by this transformation function that we have. So one way to think about is transformation or linear transformation is like a function, but there are some slight nuances that I will go into a little bit, why we call transformation rather than calling it a function in a little bit, just to differentiate some concepts that we have. So let's take this. The reason why transformation is the word that is used in with respect to linear transformation and not a function, because when we are taking input and converting that into output, this has to do with movements. Okay, so let's understand this whole idea. So again, first, transformation is like a function that takes an input vector and it converts that into an output vector that might be interested. Okay, so why we want to have a separate name, not function itself? So whenever we are talking about transformation and specifically linear transformation, it essentially, okay, so why means and is associated with the movement of a vector. So let me first of all, try to explain this concept geometrically. Let's say you have an input vector. Now you apply some transformation on this input vector. What you are going to do is you are going to change this vector and there will be new output vector as a result of this transformation. Okay, so what you saw here that initial vector moved, probably changed the shape and also location, and it moved, and this movement is associated with this word transformation. Whereas when we are dealing with functions, right, the representation that we have with respect to the function, let's say if this is x-axis and this is one variable function that we are talking about, and this is fx, typically the notation or the representation of this, something like this, is a graph, right? Is a graph, and that's what we plot. And there is no movement associated with this graph. Okay, so we take an x, we pass that as an input, and that gives me an output, and if I plot the output, this gives me a graph. Whereas when we are talking about transformation, it essentially take an input and it transforms that input in a movement. And that's why, to differentiate this concept where something can be represented as a graph and something that could be represented as a movement, even though both are essentially synonymous or a very similar concept, we use the word transformation instead of using function that we use. Okay, so that's the it's basically very similar, but since transformations are done to vector and they have geometric meaning, and that meaning is essentially a movement sort of connotation, that's why we use the word linear transformation. So let's carry on this discussion and let's discuss how linear transformation is actually carried out. So if we consider transformation over overall grid, then every point on the grid moves to its corresponding transformed location. So let's say if we have initial 2 points which are located on the Cartesian coordinate, right? And let's say these 2 points represent the tip of the vector, which we have discussed in the previous class. So from connecting from 0, which is the origin, to this will basically give me the vector corresponding to this location, and similarly this will be the vector. Right now, if I do some transformation and if I transform this, I take these 2 points into, and if I do the same transformation on both the point, right, our Cartesian coordinate will be also changing, and these points are also going to be moving, right? So the group, right, the grid move according to the corresponding transformed position. So let's go a little bit more details about how this is carried out, and have some more geometric intuitions behind the linear transformation. So what are some good properties of linear transformation? When these grids are changing, the grid lines still must be parallel to each other. And if you have a transformation in which you cannot enforce this constant, which is the grid lines are not parallel to each other, then you have a non-linear transformation and you do not have a linear transformation. Okay, and then the second constraint is that even though the grids are changing and still they are parallel to each other, the origin must remain fixed, and the location of the origin itself is not changing. That remains fixed. So these are the, if you satisfy these two conditions, and if a transformation satisfies these two conditions, then you have a transformation which is known as a linear transformation. Okay. So again, the one that I simulated before in this, when we perform the transformation of the initial axis, you can see the lines are still parallel to each other, right? Unlike previous one where it was perpendicular to each other, we do not need to have that constraint. It could be any angle. The angle between the two unit vectors, or the two axes could be different than 90, but each of this grid line has to be parallel to each other. So this is parallel to this, and these two lines are parallel to each, and if you enforce that constraint, then you have what is known as the linear transformation. Okay, so to understand the transformation numerically, it essentially depends upon two unit vectors I and j, what we do is we want to find out where I and j lands after transformation, and depending upon the transformed position of I and j, we will also transform each of the vectors. So let's try to understand this concept that we have here. Okay, so let's take an example. So if let's say if I and j are our unit vectors, so these are the unit vectors that we have. Okay, and if I have a vector in this grid, which will be located somewhere right here, so this will be the vector that is denoted by 2 minus 1. Okay, let's see if we apply transformation to it, what are the things that happens. Okay, so in order for us to understand the transformation, one thing that I want to repeat is typically, and this is something that I will finish with, is when we are transforming a vector, we are essentially multiplying it with a matrix. So let's say what we are doing, if we apply this matrix to the unit vectors of the initial grid that we have, let's see what happens to those unit vectors, because that will help us geometrically understanding what is going to happen to the actual vector embedded in that space when we transform it by this matrix that is given here. Okay, so let's go on. So let's say what happens when you multiply the unit vectors I and j with the matrix, what it essentially means that you take, especially for a two-dimensional case, you take the first column of the matrix and you multiply that by I, and you take the second column of the matrix and you multiply that by j, and that gives the transformation. So let's understand this in a geometric way. So initially, what I was there, I was essentially in this direction, this was I. Now when I did apply 0 2 and multiply 0 2 to I, the I was transformed, or this unit vector that was there in the previous grid transformed and it came here. Okay, similarly, the second column corresponds to the transformation of the j unit vector. So in the previous, right, before applying this matrix or before applying this transformation, j was right here, right, this one unit, but now it has scaled, it has become bigger in the magnitude, and it has rotated, and the unit vector corresponding to this multiplication by matrix is given by this. So now this and this becomes the two axes in which we should be representing a given matrix, given vector. Okay. So again, so this 2 becomes the primary axis after transformation, and that's what we are going to be gridding now. So now this becomes the new grid, and that is the transformation that has happened to the unit vectors I and j by applying this matrix on top of them. Okay, so let's move on. And what happens to the transform vector? The vector which was right here in the previous case, now in this case it will be also transforming. So let's see how we can derive and how this transform vector is coming at this location. Okay, so here, since the vector was 2i, 2 times I and 1 minus 1j, so 2 times I, which is this in the new transformed coordinate, the I is this, that's why 2i will be this, and the new transformed minus minus 1 will, since 1 is in positive is in this direction, minus 1 will be in this direction, that's why we have this component. So that's how the transform vector will come into picture based upon the transformed new unit vectors that we have, which has been gathered or which has become transformed because of applying the matrix that we have here. Okay, so to identify the transform vector numerically, what we do, first we take the vector, we see what are the initial unit vectors. So we have 2i minus 1j. Okay. So the transform vector will be 2 times transformed of I minus 1 times transformed of j. What is transformed of I? As I said, that first column of that matrix multiplied by I, and then transform j would be the second column multiplied by j. So similarly, if you take that, this one and this one here, we have to write 2 times 0, 2 minus 1 times 2 minus 1. And if I do the simple numerical calculation, then the transformed vector v will come out to be 2, 5. And this is the numerically way of implementing what happens to this vector if you multiply this vector by the matrix which was given here. So if I take this matrix which is 0, 2, 0 minus 2, 2, 1, and if I apply that to a vector that matrix will essentially transform this vector, and numerically this slide essentially shows what those calculations are. So if I want to do it numerically, this is the process we have actually carried out to determine what is going to be the actual location of the vector 2i minus 1j after transforming it with the matrix given in the previous slide. So let's try to understand again all of these operations geometrically so that we have some intuition about this transformation. So what happened after transformation? To the unit vectors, the I unit vector moved here and got transformed, and right, the j vector which was originally here got transformed and it basically became here, and we have a new grading system, right? So that's the transformation effect, and the transform vector which was right here came and got transformed and came here. Okay. So again, this is 2 unit here, and now in the original space you can see this is the grid, the original, the blue grid that we have. This is 2 units in I and 5 unit in j, and that's how we arrived at 2, 5. So this is how we interpret what is happening to the transformation and what we are doing to transformation when we are doing things. Okay. So in general, we typically have a matrix which defines the transformation. And here is the point that I want to stop. Remember on the function idea that I've talked about. In function idea, you need to have some specific function, something like this, which defines how should we do input to output mapping. When we are talking about transformation or specifically linear transformation, then essentially instead of having a specified explicit function which is in equation form, we have that this linear transformation function is essentially a matrix. Okay, so the matrices are functions that takes a vector, input vector, and transforms that into an output vector. So what I'm trying to allude to this is the matrices are actually a function, and they are actually a transformer, and they actually take input vectors as an input, and they transform and move them to some other location. So you can start thinking about matrices as a functions too, but the only thing is like they take typically inputs which have geometrical meanings and they move them to some other different location. Okay. So let's carry on this discussion, and what we do, again summarizing, first column of this 2-dimensional matrix will be basically transforming the initial unit vector in the I direction. The second column will be transforming the initial j unit vector that we have. Okay, and when we apply this transform to any vector, okay, what we have, then we have essentially that is represented by this product matrix multiplied by this vector, which essentially could boil down into this simple calculation. So you take x and you multiply individually with the first column, you take y, multiply them with the second column, and then you add them up and you will get this definition, or which is px plus qy and rx plus sy. So what happened? This xy has transformed, and now this is also a 2-element vector, and the element now are taking into the other numerical aspect that is imbibed in the matrix, and using that to transform this xy into a new vector which is given here. So that is what the linear transformer are, and that is what linear transformation geometrically means. Okay. So what is linear transformation? Essentially it's a vector matrix multiplication operation. So you take vector And then a matrix acts as a transformer or synonymously acts as a function which takes that as an input, and then it outputs a new vector, and that new vector is essentially the movement of the initial vector by which has been transformed by the matrix that you have. So that's the geometric intuition behind the transformers, linear transformer.